All right, welcome to Chapter 5. Chapter 5 is called Analytic Trigonometry. There will be two very important things for this chapter: your unit circle and the purple sheet, which you're going to get today. Call it the purple sheet because it'll be on purple paper. So section 5.1 is using fundamental identities. So on your purple sheet, you have all these identities. We have the reciprocal identities, the quotient identities, and the Pythagorean identities. Take a look at them, become familiar with them, because that's what we're going to use. We're also going to look at the cofunction and odd and even identities today. So keep these handy. We are going to take crazy trig expressions and rewrite them in a simplified manner. So if I see something like sine of x times cosine squared of x minus sine of x, I say, oh, I could factor out a sine of x. And that leaves me cosine squared of x minus 1. Well, cosine squared of x, that looks a lot to me like one of my Pythagorean identities. But let's take a sidebar. The Pythagorean identities, we have sine squared plus cosine squared equals 1. I want cosine squared minus 1, so I'd subtract that 1 over. But I'd have to get that sine squared out also. So cosine squared minus 1 equals negative sine squared of x. You can rewrite any of your identities like that. So sine of x times negative sine squared of x, which makes negative sine cubed x. There's our answer. Cosine squared of x times cosecant of x minus cosecant of x. All right, well, I can factor out a cosecant of x, leaving me a cosine squared of x minus 1. Oh, and I just figured out that that will give me negative sine squared of x. This one is a little more complicated because I know cosecant of x is 1 over sine of x. And remember that negative sine squared of x is secretly over a 1, which means one of my sines cancels from the numerator and denominator, leaving me just negative sine of x as my fully simplified version. All right, secant squared of theta minus 1. Well, I know secant squared of theta is equal to 1 plus tangent squared of theta. So I can plug that right in and keep that minus 1. Oh look, plus 1 and minus 1 cancel, leaving me just tangent squared of theta. For this next one, we have to get a little creative. We are going to factor. If this said 4x squared plus x minus 3, we would dive right into factoring, right? 2 sets of parentheses, 4 and 1 or 2 and 2. I'm going to go 4 and 1, 3 and 1, positive 4, negative 3. Easy, we've done that. Instead of x, we just have tangent of theta. So it's really 4 tangent of theta minus 3 times tangent of theta plus 1. So we can also factor it. All right, let's factor this next one because I know I could rewrite it with sine, but I can also factor it. This is just a difference of squares. 1 minus x squared would be 1 minus x times 1 plus x. We don't have an x, we have a cosine of theta. And the reason we're talking about that instead of rewriting it as a sine is because that could help us sometimes being able to do that. All right, for the next one, I have 2 cosecant squared of theta minus 7 cosecant of theta plus 6. I don't see any GCF, so we'll dive straight into factoring. To get 2 something squared, we take 2 cosecant of theta and 1 cosecant of theta. To get 6, I can use 6 and 1 or 2 and 3. To make 7, I think I need to use 2 and 3 because that makes a minus 4, minus 3, and there's my factored answer. All right, now our factoring is going to get a hair trickier. So I have cosecant and cotangent in the same expression. I can only deal with one trig function at a time. But I happen to know cosecant squared is 1 plus cotangent squared. So I'll plug that in. And keep that minus cotangent of x minus 3. Combine my like terms, I have cotangent squared of x minus cotangent of x minus 2. And now I can factor. Cotangent of x and cotangent of x. To get 2, I need 2 and 1. It's minus 2 plus 1. Same thing with this next one. Secant squared of x plus 3 tangent of x plus 1. Secant squared is 1 plus tangent squared of x plus 3 tangent of x plus 1. Combine my like terms, I have tangent squared of x plus 3 tangent of x plus 2. First thing in each set of parentheses will be tangent of x. I need a 2 and a 1, both positives. There we go, fully factored. All right, now we get into the real fun. I don't have a GCF that I can take out. I don't have anything I can factor. I just am stuck. When in doubt, I would recommend change everything into sines and cosines. So sine of t plus cotangent is cosine over sine times cosine of t. Well, I can combine these two pieces together to make sine of t plus cosine squared of t over sine of t. Now I have some options. I personally would say, let's get a common denominator. So I'm going to multiply this fraction by sine of t over sine of t. When I say fraction, remember it's got that invisible 1. So I now have sine squared of t plus that cosine squared of t I had before, and it's all over that common denominator of sine of t. And I know sine squared plus cosine squared is 1. And now for these to be fully simplified, you don't want a fraction anymore. 1 over sine is cosecant of t. All right, the next one, I have cosecant of x minus cosine of x times cotangent of x. When in doubt, turn everything into sines and cosines. So I have 1 over sine of x minus cosine of x times cosine of x over sine of x. I can combine that, so I have 1 over sine of x minus cosine squared of x over sine of x. And I can combine those into one fraction because they have the same denominator already. And 1 minus cosine squared is a version of my Pythagorean identity to give me sine squared of x. And sine squared of x over sine of x is just sine of x. And there we have it. All right, now we're getting into fractions. I look at my fractions and I don't see anything I can do. So I have to get creative. Several ways to get creative, but when you see a 1 plus a trig function, one trick is to multiply by the conjugate. So multiply the numerator and denominator both by 1 minus cosine, in this case. So in the numerator I have sine of theta times 1 minus cosine of theta all over. When I multiply this denominator out, it's a difference of squares. It's 1 minus cosine squared of theta. And I didn't do anything to the second fraction yet. It's just along for the ride right now. 1 minus cosine squared of theta is sine squared of theta. One of my Pythagorean identities. And then I see, oh, I can cancel a sine of theta from the numerator and denominator, leaving me 1 minus the cosine of theta over sine of theta plus cosine of theta over sine of theta. And now I can combine my like terms, or not my like terms, sorry, combine my fractions because they have the same denominator. The cosines cancel out, leaving me 1 over the sine of theta And we know that is cosine or cosecant of theta. All right, for the next one, I noticed that both fractions have a denominator that's one portion of the conjugates of each other. So I'm going to multiply them both. So the 1 plus sine of theta, I want to multiply by 1 minus sine of theta on the top and bottom. The 1 minus sine of theta, I want to multiply by 1 plus sine of theta on the top and bottom. So my first fraction becomes 1 minus the sine of theta over, when I multiply that out, I get 1 minus the sine squared of theta. Plus, my numerator of the second fraction becomes 1 plus sine of theta. And my denominator becomes 1 minus sine squared of theta. My fractions have the same denominator now, so I combine them. And I get 2 over 1 minus sine squared of theta. I still have a fraction. That's not fully simplified then. 1 minus the sine squared of theta is a version of the Pythagorean identity, giving me cosecant, or wow, cosine squared of theta. And now 1 over cosine is secant. So 2 over something just puts a 2 out front. 1 over cosine squared would be secant squared. So 2 secant squared of theta is our simplified answer. All right, to simplify this next one, it looks like it's pretty darn simple already, but we want to get no fractions. So I'm going to multiply the numerator and denominator by the conjugate. Anytime you see 1 plus or minus a trig function, you're probably going to want to deal with that conjugate somewhere. So I get 1 minus sine of x over 1 minus sine squared of x. 1 minus sine squared of x is cosine squared of x. All right, now I'm going to rewrite this as two separate fractions. 1 over cosine squared of x minus sine of x over cosine squared of x. 1 over cosine squared of x is secant squared. Sine over cosine is tangent, but that leaves me still an extra cosine in the denominator. So I have secant times tangent. So I have secant squared of x minus secant of x, tangent of x. I could also factor out a secant from both of these and have secant of x times secant of x minus 1, or tangent of x, however it works. All right, for the next one, cosine squared of x over 1 minus sine of theta, theta not x. I actually would not multiply by the conjugate for this one, because I know cosine squared can be rewritten as 1 minus sine squared. And I know that 1 minus sine squared of theta can be factored into 1 plus the sine of theta times 1 minus the sine of theta. And now my 1 minus the sine of thetas cancel, leaving me just 1 plus the sine of theta. So that's a tricky one to get used to. And then let's talk about logarithms involved also. Natural logs. I have two natural logs added together. I can smush them together into multiplication. So I have the natural log of cosecant of theta times tangent of theta. Oop, absolute value, sorry. Now I can combine these two fractions. Well, trig functions. Cosecant is 1 over sine. Tangent is sine over cosine. Those sines cancel each other out, giving me natural log of 1 over cosine of theta. And 1 over cosine is secant, so this is the natural log of absolute value of the secant of theta. And we'll follow the same idea here. Natural log of secant of x plus natural log of sine of x, we can smush those into 1 by multiplying them. Secant is 1 over cosine. When I multiply those together, I get natural log of the absolute value of sine of x over cosine of x. And sine over cosine is tangent, so natural log of the absolute value of tangent of x. All right, we're going to pause this video there.